Okay, David, let's crack on with the second set.
Okay, welcome back, everyone. Hopefully we'll have a slightly smoother run of it in this session, but the next up, we've got a couple of projects from the gas networks. The first one is Intelligent Gas Grid. And then hopefully, if we get through these two with some time to spare before the final Q&A, we'll come back to the Eye in the Sky project later on. There's been some scheduling issues with the parallel series that's going on for whole system integration as well. So I think that's what's caused some of the problems. But over to you, Tom.
Fantastic. Thanks very much, Dave. So if we have the next slide, please. Great, thank you. And one more as well, please, Dave. Thank you. Fantastic. So hello, everyone. My name is Tom Jeffries. I'm Head of Product Management at Autonomy. We were SGN's project partner on our discovery phase Intelligent Gas Grid project. I'm very pleased to be able to introduce the project to you this morning. So the ultimate ambition of the project, sorry, if you go, yeah, fantastic. The ultimate ambition of the project is to realise an intelligent gas grid. Now, the data and digitalisation challenge seeks solutions to the complexity and the scale of achieving net zero using modern digital technology. Our project addresses this challenge by defining a vision for digitalising gas network activities, which will inherently contribute to better coordination, planning, network optimisation, which are all key management functions for gas distribution networks. In the discovery phase, the project developed an impact assessment framework, which evaluated a number of potential intelligent gas grid use cases. We're going to explain these use cases in more detail and present the assessment over the coming slides. And then we're going to explain how we're intending to progress those use case development in Alpha. Each of these use cases prioritises the challenge initiatives of saving costs to consumers, decarbonising the energy supply, improving customer experience, and trying to increase operational efficiencies. Now, the intended use of AI and machine learning techniques, which is essentially the sort of principal innovation behind the project, we feel fully exemplifies the challenge-specific scope of using novel data and digital platforms to improve network planning, network modelling, network forecasting. We believe that these solutions would inherently, constitute genuinely novel methods. And what we're intending to do is complement those data-driven solutions with modular dashboards that integrate solutions with data analytics, and essentially present those as actionable insights back to the gas network management personnel in charge of the networks. Next slide, please, Dave. Thank you. So over the last few years, SGN and Autonomy have established a very close and effective working collaboration on a number of innovation projects, not least of which is the Pressure Control and Management NIA project, which was also joined by Wales and West Utilities in the second phase. That project has now completed and is just beginning to make that critical and sometimes challenging transition from innovation and into production. That rollout we're hoping is eventually going to really put a lot of distributed network sensors and communications technology into the low pressure gas distribution networks. And that in itself represents a step on the journey of network digitalisation. As that progression continues, and the feedback we've got from many of the people that we've explained the project to, is that really presents an opportunity to really harness, capture a lot of data about the networks. And the challenge that we're exploring under this project is how best to use that data to go forward, to solve more, or to improve more about the network management using that data as the input. In parallel to the Pressure Control and Management project, Autonomy have also worked with SGN on some early field trials of a machine learning based approach to optimise pressure control with a focus initially on methane leakage reduction. And it's through that work that Autonomy first became involved with Faculty AI, who are one of the leading AI consulting and technology providers. So I'm now going to hand over to Andy Perry from Faculty, who's going to give you more of an insight into their experience and capabilities, and also go through and present the findings of this discovery phase. So over to you, Andy.
Hello, and can you hear me okay?
Yeah, we can hear you fine, Andy.
Yep, lovely. So I'm going to give just a brief intro to what we do, and then I'll hand over to Andrew Glennie, who'll go into some more detail on what we did in the project. So Faculty, we are an applied AI services business. So we custom design, develop, build, and deploy AI solutions for our clients, and we're very excited to be part of this piece of work, which is genuinely groundbreaking, I think, in the way that we are applying our types of machine learning concepts into the gas grid. And we've done this across a number of opportunity areas within this initial discovery phase. I think what's very interesting about this piece is that it will be about how do we combine opportunity areas. So how do we combine those use cases and think about optimized decision making across different applications of pressure management. Just go on to the next slide, please. Thank you. So in terms of the way we like to work and the way we're sort of approaching this piece, we like to think about business solutions. And in terms of that sort of business problem that we begin with, we think backwards in terms of what actions can be taken to affect that problem, what decisions can be made to affect those actions, and then working back from those decision-making sort of optimizations, like what are those forecasts or what's that understanding of the system that's required in order to optimize that decision making. What we've done in this piece, so in this discovery phase, is basically look across 8 opportunity areas for the gas grid for SGN, and for each one thought through the problem statement that we're trying to meet, thought through how pressure management control on an automated basis could help solve that problem statement. And then thought through, based on data availability and also sort of commercial impact, where the feasibility and commercial opportunity is for each of these use cases. And through doing that, then designed a high-level solution for each one that could be taken forward into alpha. So the core kind of approach within discovery has been about assessing that commercial impact on a relative basis, but also understanding the relative complexity of implementing a solution based around sort of a machine learning approach. We then created a plan that combines these into an approach for alpha. And in particular, what we've been thinking about within alpha is, on one hand, how do we ensure that there's a holistic view here so that we have that ability to think about these use cases in the round, think about the trade-offs between them, and so any solution that's created allows that type of trading off of how pressure management is applied across these different use cases. And also with alpha, we're trying to make sure that we keep a breadth of opportunity that we can analyze, while also taking some of these opportunities through into a prototyping phase, so that we can think about both how they integrate within the gas network system, but also show some genuine results of based on backtesting of how these use cases actually perform. I'll stop there and just hand over to Andrew Glennie, who's going to go into a bit more detail about how we actually did that within discovery.
Great, thank you, Andy, and I hope everyone can hear me okay. Thanks very much, everyone, for joining this morning. I'm Andrew Glennie. I'm a senior manager with the faculty team, and I've been helping to put together our outputs for this discovery phase and also in our planning for the alpha phase as well. I think one thing I'd really reinforce that Andy mentioned is that, at this stage, we've really tried to identify, how can we maximize, using the power of AI and the data held by networks, how can we really maximize the remote pressure control provided by Autonomy? And this really does have potential to be, an industry standard. And this phase is really trying to show how those benefits can be delivered. And that's really how we've sort of approached this phase, and also in our planning for alpha phase. What's on this slide here is the set of use cases in a little bit more detail that we identified in this discovery phase. And and I won't go through the full details for each, but just quickly to kind of run round. If we work clockwise, I mean, the first case, as Tom was referencing, is around reductions in methane leakage. Can we essentially better predict downstream demand to optimize the pressure and essentially reduce leakage? How can we alter pressure to maximize feed-in of renewables, and how can we, produce a prediction for escape distributions and reduce subsequent escapes? I think use cases 4 through 6 are very much around how do we improve network management. So use case 4 around detecting faults, essentially. Use case 5 around detecting network excursions. And use case 6 really around dashboarding and ongoing monitoring of the network, which would enable the network to essentially better coordinate resources, which essentially not just improves operational performance, but potentially benefits for customers and wider environment as well. Last 2 use cases you have there, 7 and 8, are predominantly around sort of cost efficiency. Can we use AI combined with remote pressure control to allow for mains replacement by insertion instead of open cut? And similarly, how can we look to improve reinforcement capex efficiency by better essentially extending the life of an asset using this remote pressure control tied with artificial intelligence? And I think one thing I'd also reinforce from what Andy mentioned is that these shouldn't be thought of as a set of standalone use cases. The power of AI here is really in cases of trade-offs, and how can we optimize across at least a subset of these, if not all. So, in cases where there might be cases where you want to lower pressure to reduce leakage. There might be cases where you need to increase the pressure. For example, if you're putting a greater extent of blended renewables through the network, how can you actually optimize this trade-off? So I definitely emphasize the commonality across these and the benefit of AI being in how can you come to that kind of global optimum rather than an individualized set of 8 individual use cases. Go to the next slide, please. Yes, step 2, there we go. So this slide here is an example schematic of this next step, which is around how can we, once we've identified these use cases, how can we initially design an AI solution for each of these? And this is an example for opportunity area 4, which is around understanding network performance and condition. So this phase is really trying to set us up for alpha and development of a proof of concept and making us comfortable of all the requirements at each step of this end-to-end implementation process. So around, what are the data requirements? Around, in this case, we've got, say, fault information and near real-time pressure log data. What are the questions we can look to answer? Moving on through the diagram, what is the types of analysis that we can be looking at here? In this case, are there potentially unusual patterns of signal data that we need to be picking out? And into development of a proof of concept, which would show how this can be implemented in the network. Again, as some of the previous presentations have also mentioned, I think the key thing here is not just coming up with a good AI product and a good, optimizing the AI model, but also optimizing how this is implemented within the business. And that last stage there really is around deployment of any output. How can we actually optimize how this is used at SGN? How can we make sure that the users of this tool can interact with it, and how can we ensure that insights are translated into business decision making? And so that's just an example of the flow through and analysis that we did for each use case. If we go to the next slide, please. If we flip. Hasn't quite updated on my screen, the next slide, but I wonder if that might be an internet.
Yeah, we can see slide 3, Andrew. So.
Okay, this is up. Yeah, it's updated for me. Fantastic. So what you see here is the output of our really our output of our work at this stage. And this is around how can we produce a hierarchy of use cases? How can we essentially assess cost benefits of each one. And we've come up, this chart here is really the output of that. And if I explain a little more detail, so on the x-axis you have complexity, and as you go further to the right, you go lower in terms of complexity. And what we're really looking for here is use cases that are relatively lower complexity, but also relatively higher impact, which is on the y-axis there. So the higher up the y-axis, the more potential impact that we've assessed and be delivered through the use case. What does impact and complexity really mean? So if I start with impact, we've identified four main channels by which impact can be delivered through these use cases. One around cost savings and how we can extract cost from the business. One example being that tasks that you wouldn't necessarily need to set governor pressures manually could be automated. That's an extraction of cost potentially from the business. How can we deliver carbon reductions or carbon equivalent reductions, which is obviously a benefit in line with our environmental goals, but also an area that customers really value, as some of SGM's business plan for GD2 research has shown. Can we improve customer experience by better network planning and operation, and essentially reduction of disruptions to the network? And also within the existing cost base, how can we drive operational efficiencies? So for example, if we have a dashboard which allows you to better coordinate resources, that can therefore drive better efficiencies within kind of network planning and operation. In terms of the complexity, I mean, this can really be thought of a kind of quasi cost of implementation. There's a few factors you can see on the right there. So solution feasibility, which is really around, can a technology solution be delivered that ultimately delivers the requirement? Development effort, namely the resources needed to put in. Data availability, assessing what data is available now and also what data is planned in future. And the last two around production suitability and operational execution, around can a solution be easily deployed and scaled? And lastly, can it be translated easily into business outcomes and essentially action? And what you can see here is there are essentially two groups of use cases that we found. One of relatively lower complexity and higher impact, and a set of relatively higher complexity and slightly lower impact there. And the three that we found around the relatively higher impact and low complexity are around reductions in methane leakage, the reduction in escapes, and also around KPIs and dashboarding. And all of these demonstrated strong potential in terms of benefit, in terms of, in the case of methane leakage, in terms of reductions in, namely reductions in methane to the environment, and similarly with escapes, but also demonstrated that there was solid data availability within the business, and these could also be translated relatively seamlessly and clearly into an output that could be used by business users to drive better business performance. Next slide. Thank you. So what does this all mean? So we've taken that prioritization really to inform our alpha planning. And our approach here is really to take a bit of a step back and think, where do we need to be at the end of alpha to then drive a successful beta? And that means, where do we really need to be such that we're ready for deployment and scale at beta phase? And what are the activities that inform that? And I think the answer to that is really that we need to be in a place in alpha where we've got working proof of concepts for a set of use cases that really demonstrate the value that can be delivered. Now, naturally, that's not possible for all 8 use cases that we've identified with the time and resource available, but that's where our prioritization framework comes in. And what this chart here shows is a general planning methodology, but also shows the distinction between the priority use cases versus the other use cases that we identified. And the difference really is that for the priority use cases, we'll be looking to develop a more advanced proof of concept that can then be scaled at beta phase. So for around the methane reductions, for example, and the escape distributions. and also a tested wireframe for the network dashboarding and ongoing KPI monitoring. Whereas the other use cases will still be continued, analysis will still be conducted, but this will be mainly around data assessment and around preparing ourselves for any potential implementation. Last thing I'd say on this is that I've sort of come at this so far from a data science perspective. I think a key work stream here is around what I was mentioning previously around how can we actually not just optimize the model, but actually optimize how this is integrated within the business. So at Alpha, we're looking to conduct some further user research, actually engage with users to help inform the development of prototypes and proof of concepts, and also in our planning for beta phase, how can we actually take these, scale them up within the business effectively. Last slide.
Just one point to just add to that, Andrew. So I think within Alpha, within that business integration, what's very important for us is to make sure that we're able to both have a live connection of those models from data pipelines, from SGN systems, but also to be able to integrate back into a user interface that's very functional and allows that trade-off between different uses. And I think one of the exciting things that could be achieved through this project as we go into beta, if we're able to get there, would be that kind of link of commercial and operational decision making within the network. So there's kind of 3 layers to this. Like on the base layer, like an individual opportunity area could be optimized. So like one of those use cases, you're able to make an optimal decision about how pressure control is used, let's say to control methane leakage. Like one level above that is, well, okay, operationally, can we trade off between a couple or more different use cases? So we think about how pressure control could be used effectively in aggregate across different uses. But then the third level is, well, let's bring in the commercial element as well, and how far actually can we bring in like an understanding of cost benefit case into that operational decision making as well, and do that across different use cases. And that feels like kind of the holy grail of where we'd like to get to in terms of this idea of an intelligent gas grid, is that you not only can trade off quite innovative solutions across use cases, but also on a commercial and operational level, be able to do that. Sorry, back to you, Andrew.
Thanks, Andy, and appreciate that we need to come to the end of our slot, so I'll wrap up quite quickly here. This slide is just some of the summary really to wrap up around the conclusions and recommendations moving into Alpha. I think, as you've seen, there are a couple of groupings of opportunity areas that really inform our prioritization. I think one thing we found is that these do share some similarities in terms of their development needs, which is a benefit for us in terms of being able to ensure that we can make progress across opportunity areas. As I've set out, there's a clear mechanism where opportunity areas can deliver benefits for customers, in some through different mechanisms, some more focused on, for example, the environmental side. Others are more focused on cost efficiencies, but there's a clear mechanism by which these opportunity areas can be translated into benefits for customers. And lastly, there's a clear link with SGN's own digitalization vision. I think the key thing here being that you can't just deploy an AI solution standalone. That needs to be accompanied by better data and wider digitalization strategies. Just moving into the recommendations for Alpha. There's clearly, as I set out, there's a couple of work streams where we need to continue to share knowledge with the business. There's that prioritization of impact and opportunity areas. There's also considerations of wider factors, obviously not just optimizing AI, but some of the safeguards around that. And in this case, really want to draw attention to some of the cybersecurity aspects, given the importance of kind of safety when looking to develop an automated network control solution. And lastly is around securing enabling technology, continuing those preparations for full rollout of the remote pressure control technology of Utah. So that's all I had. Thank you very much for listening, and look forward to any questions later on.
Brilliant, thanks a lot for that. We're hopeful that we'll be able to fit in the Eye in the Sky project after this project, so we might eat into that Q&A a little bit, but I think it's worthwhile to try and get that project presented as well. So in the interest of time, I'll hand straight over to the Predictive Safety Interventions team, which is also a project run by SGN.
Good morning, can you hear me all right? Fantastic. Hi, I'm John Haynes, the Strategic Design Lead at Field. Just quickly fill you in, Field is an operational digital twin used by a number of utilities and infrastructure companies to improve safety and productivity. Field workers use Field to conduct point of work risk assessments, where they record on-site video, and we use a combination of sort of artificial intelligence, machine learning models to interpret and format what they've said and provide their managers with the video and the hazards that they've identified. Last year, we've been working with SGN since our inception, and last year this led to a 20% drop in safety events at SGN. And I'm here today to speak to you about how Field and SGN have worked together to see whether we can use the hazards that are identified in those risk assessments to predict the likelihood of a safety event. Next slide, please. So I'm going to start by kind of walking through the problem and opportunity space. Next slide, please. So there's kind of 5 high-level problems that we identified during the discovery phase that help define the scope of our sort of proposed solution. There were 8 deaths and 2009 lost time injuries. That's when someone has to take time off work as a result of the injury that they've taken in the utility sector last year. And I used the HSE cost model to sort of cost that out, and a sort of estimated cost to society, government, employer and individual of £160 million. Health and safety managers are currently relying on a 90-year-old theory to gather data about indicator incidents to make incremental improvements to safety. I'll get onto exactly what that is in the next slide. Number 3, as a result, workplace safety has plateaued for the last 8 years. So despite advances in technology, there's been no real paradigm shift in workplace safety. And that's actually across all industries. It's not just utilities. So there's quite a large scope for improvements to be made there. Number 4, it will cost the utilities industry an estimated £111 million a year in wages just to capture data about those indicator incidents. Again, I'll get onto that in a second. But we use kind of weighted average salaries to cost up exactly what it would take just to capture data. And number 5, the data that is being captured around safety incidents, apart from the most severe incidents, everything sort of underneath a lost time injury, the data that's being captured is generally fairly poor quality at best, and there is no standard, there's no way for this data to be shared across the rest of the industry. So even if one company is capturing really good high fidelity information about all of these indicator incidents and less severe incidents, there's no way for that data to be shared across the sector. Next slide, please. So onto that theory that I was talking about. So what we found out is health and safety managers are using something called the accident triangle, which is essentially just like a ratioed relationship between safety events of different severity. So we use the ratios to calculate the rates that events should have occurred and should have been reported. So what this means is there's 400 lost time injuries for every fatality, 20,000 minor injuries to every 400 lost time injuries. So you can use those ratios to work out in terms of the number of reported injuries and reported near misses and unsafe acts, what should have been reported. And this data is what health and safety managers are basing all of their process changes around. You know, they're trying to capture information, specifically, you know, capturing a fatality or capturing an injury of some type. It's very obvious what the outcome is, very obvious what to record, and in often cases the kind of cause and events leading to that incident can be deduced. You know, you can kind of reverse engineer the situation and work out what happened. The belief with the accident triangle is, though, that there's these indicator incidents, near misses and unsafe acts that occur at quite a high rate. That if you can gather information about those indicators, those near misses and unsafe acts and conditions, and make a reduction to those, like a meaningful reduction to those, then you'll have like a trickle up effect. So, you know, if I can reduce the number of unsafe acts that occur on my work sites, I will have a net effect on the number of injuries and fatalities that there are. So what you can see in the middle is SGN's reported, like actual reported figures in black, and then the delta based on the number of lost time injuries and using the ratios, the kind of delta of what they should have captured. And then using the utilities industry figures on the right hand side, you can kind of see that there should have been 18 million indicating incidents reported last year. But obviously, because there's no way for people to share that information, or companies to share that information, we don't actually know whether that was the case. Next slide, please. I'm not going to go into these quotes. You can read them. But when we spoke to managers across, across the organisation at SGN, what became really evident was that actually identifying indicators is really difficult, firstly, and that even when people are provided training to recognise it, there's quite a low incentive to do so, because there's a bit of a dichotomy. The same people that you're asking to report these incidents are the same ones that you're also asking to reduce them. So there's that, and then also there's a bit of a bell curve. As people get more experience, they start to they report more of these indicators, but then as they become as they become more experienced, actually they also become a bit more complacent, and as a result, the average length of the description at SGN for near misses and unsafe acts and conditions last year was just 260 characters. So the length of a tweet, we're supposed to be able to deduce exactly what happened and base our potential process changes on that. So there's a lot of projection and a lot of experimentation when it comes to using these indicating incidents as a method for creating process change to meaningfully reduce the risk of safety incidents. Next slide, please. And so we also sort of weighed up the commercial opportunities of this. So obviously, reducing time lost to injury, £165 million is the cost of the lost time injuries. That's a sort of overall societal cost, but that also resulted in more than 10,000 days lost to injury last year, at least. The figures don't report the exact time taken off. It's split into two categories: 6 or less days, or 7 or more. So that's a very conservative figure. It could be much higher. Reduce the cost of data collection. So just using weighted wages, just weighted salaries, and roughly 6 minutes per report, which is the time it takes, on average, workers at SGN, field workers at SGN, to report near misses and indicator incidents. We used that. We applied it to the 18 million incidents, and the weighted salary gave us a cost of £111 million a year just to capture that data. Obviously, that doesn't take into account training, incentivization, etc. That is just literally the time it takes to pull my phone out and record the fact that something happened. Last year, Thames Water recorded for one site over 4 days, one work site, and I'm talking like one set of barriers put up on a street, £100,000 in penalties because of the safety risk that it presented to pedestrians. Pedestrians were being forced out into the road. So it's £100,000 just in one work site for 4 days. What we've worked out is the Predictive Safety Interventions project, in order to recoup 100% return on investment, including our alpha plans, we only need to prevent 7 lost time injuries at roughly an £82,000 average cost. To recoup that, obviously, if we reduce a couple of fines as well, then that could be expedited. Next slide, please. So next, I'm going to get on to what we learned and what our findings are. Yeah, that's fine. Yeah, you can skip to this one. So what we did was we started by sort of looking at the data that we had. So the yellow boxes indicate something that field has captured in a proprietary manner, and all the grey boxes were data sets provided to us by SGN. In fields, we captured the hazards via the point of work risk assessments. jobs, so details of the work completed, the people on the jobs, etc. And blockers, which is just a sort of marker to show that work has stopped, which might be an indicator for an incident. And then SGN provided the actual safety incidents themselves, vehicle telemetry data, repairs and assets, so that we could see which sort of assets were linked to any particular job, and then the org chart, which is how they kind of tie things together, is just through the surname and initial was the kind of relational value between those. A lot of this data isn't captured in field, right? So there wasn't a particularly explicit link, which meant that we were only manually able to link up 75 of 3,700 odd incidents to jobs in field. We suspect that there were many more, but it was quite a manual process. It took a number of hours. So it's a relatively small data set that we were working with, where we were able to make those links. But as you'll see in a second, we had some quite encouraging results. So next slide, please. So we found evidence that predictions can be made, right? Just by tying together those risk assessments and the incidents. We found evidence of really strong sort of correlation, and also negative correlation as well. So in the cases of some of the strong ones, in one case where we linked the risk assessment to the safety incident, the thing that was damaged in the incident was identified in the risk assessment. The mechanism of damage was identified in the risk assessment, and the root cause, the inability to see the thing, was identified in the risk assessment. This is really encouraging and shows us that risk assessments are, are a good input for a predictive model. Next slide, please. Next, we took a look at the relationship between risk assessments and safety events. And we found evidence that safer behaviour might lead to safer outcomes. So we took a look at the number of incidents recorded by at depot level. So SGN depots, the number of incidents that they're recording on any given day, and the number of risk assessments that are being recorded on any given day. And we found a statistically significant inverse correlation between the number of risk assessments and incidents. So what that means is on days where there were more risk assessments being done, there's less safety incidents being recorded. We don't know the cause. We don't know which way round it is. We don't know whether, recording more risk assessments leads to less safety events, or whether, a safety event has occurred and thus then they're unable to record risk assessments. It's likely that there's a mix of the two. But we found this quite encouraging, particularly because it was statistically significant. We ran the incidents through some machine learning models. We found we tested 15 different types of machine learning model. We found 2 that showed the most potential. There's the naive Bayes model and logistic regression model. Both models achieved a recall. We only tested for recall. We didn't test for precision because of the number of sort of linked. Our data set was quite small, so we weren't testing for precision necessarily, but both models achieved a recall of more than 50% on multiple occasions, which is very encouraging considering it's quite a small data set. And we can see the potential for machine learning, a machine learning model being used to predict incidents. Next slide, please. We also, so we worked with 3 partners, 2 external partners. We have our own sort of internal machine learning engineer, and we worked with 2 external partners to analyze sort of all of these data sets. One of them took it upon themselves to look specifically at the relationship between sort of safety incidents, location, and driver behavior. And what we found is that harsher braking events are an indicator that safety events are going to take place, so that we can definitely use that data to help as an input for the predictive model. And also location, 45% of safety events at SGN last year took place in 10 postcodes. So location definitely has a relationship with safety risk. To summarize this preliminary study, correlation analysis has shown the relationship between locations, weekdays, and hazards. and we think we'll be able to use that to sort of power our predictive model. Right, next slide, please. So on to our vision and kind of next steps. So our solution, our proposed solution is a predictive...
If you could, John.
Sorry?
1 minute to wrap up if you could.
Great. So our solution is a predictive safety system that will analyze which actions contribute the most to safety, worksite safety, productivity, and amplify them across the network. Next slide. If we take a look at how this will work, we'll assess the risk level of each work site, we'll suggest interventions at lower risk level, we'll learn strategies to improve safety and productivity, and that will cycle, and we'll share the knowledge between all field users. Next slide. And this is the last bit, apart from photos of the team, is so the next step. So as we move into alpha, we want to improve the quantity and quality of the data. So we're going to capture more stuff proprietary and field. We're also going to trial ways that we can use technology to help capture near misses and the rest of those indicating incidents. We're going to build a system to interpret and predict risk in real time. So we want to use machine learning models to help ingest the data and interpret it. And we're going to build a risk prediction model designed to assess every work site. And then we're going to demonstrate possible interventions. So we're going to do a mixed reality proof of concept to show real-time interventions. And we're going to research and design how the predictive model suggestions could be used in the field app. That's it. Thank you for your time.
Great, thanks a lot, John. Really appreciate that. Some really fascinating insights coming out of that one already as well. So, Alex, do we have you?
Yes, I'm finally here.
Yeah, there's been a lot of anticipation for this, so no pressure. Right, so we'll go back to the Eye in the Sky project.
Yeah.
Hopefully we'll get time for a few questions and answers at the end of it. So if you could rattle through, Alex, and anyone who does have questions from the last two projects, if you could also answer in the chat, that should help us save some time. Thanks a lot for that, John, and over to you, Alex.
Yeah, so what we did in Eye in the Sky project, we tried to understand which satellite technologies we can use in either our asset management operations or during the extreme event conditions, how we can respond. So we got a consortium of partners. We got a National Grid Electricity Transmission and Gas Transmission representing networks. Spotted is the company that works in data analytics, satellite data analytics, Cranfield University, who are the experts in aerospace technologies and research, and ESA, who is the European Space Agency, owns and operates satellites for different applications. Next slide. We can skip this one to save time. So we looked through 12 applications which we identified that can benefit from satellite monitoring data. On the assets monitoring, we look through the bird nest detection that can nest on our transmission towers or buildings. Can we detect them? Vegetation management, can it help us to understand the vegetation growth and the risk to the overhead lines we operate? Building roof damage, can we detect any damage to the roofs or any growing vegetation, molds, and things like that? Identify any unauthorized construction or material storage close to our assets that again can bring the risk to safety of people that work there because of the proximity to electricity infrastructure or gas infrastructure, as well as potentially cause some damage to this infrastructure. Land motion risk, if it can affect underground assets due to change of the river streams, underground river streams, or change of the soil, effects of flooding, climate change, and so on. Asset movement risk, for example, any change of the assets allocation, meaning that something happening either with an asset or with the underground foundation. And can we detect hydrogen or SF6 leaks, which hydrogen is what is proposed to be used for future gas transmission. SF6 is one of our biggest carbon footprint contributors for electricity transmission. can we detect there are leaks, and basically based on that, take actions. From emergency response, we looked into can we detect water levels around the assets, basically using lifetime data to identify the risk for the assets, for example, substations, towers, or gas infrastructure, smoke and fire around the assets due to wildfires, for example. Detecting of foreign objects post-windstorm, for example, ending up inside the substation or close to our assets that can bring any risks. Damage to assets post-windstorm, again, similar approach, but detecting the damage caused, and detect any broken conductors on the overhead lines. Next one. So we looked through the different aspects for each technology. It was technical readiness level, how far is technology from being ready to be applied, the cost, how easy to integrate it into existing systems, is data available, and will it bring end user value, meaning does it have benefit, is benefit cost analysis positive or not. So through all these applications, we split them into 3 groups in the end. One group is stop, either because technology is not there, and we don't see that we would achieve acceptable level of development within SIF funding timeframe within like next 3 years, for example, or it doesn't bring financial benefit against business as usual, where business as usual in most of the cases is helicopter patrols with helicopters flying around the networks, or food patrols where people just walk the lines or transmission systems. Especially it's the case for low value for emergency response, because in what's happening in satellite industry, that if you want how it's called, requested image made, that it's very costly because they need to divert satellite to be in the right position at the right time. And that's meaning that the price of one image, let's say kilometer by kilometer area, can go up to several £1,000s, meaning that for the same amount of money, we can just send people there and see it with their own eyes. So most of these emergency response technologies failed on the cost-benefit analysis, as well as current business as usual, that those satellites can deliver you data which is about 12 to 24 hours aged, meaning that if we need, for example, for flood detection or something, it's basically what happened 12 hours ago. It's not relevant anymore at this moment. However, we detected that smoke and fire around assets is already developed into business as usual, basically using publicly available data, as well as there are several providers that can do this service. They're built on the case of fires in California, and for them it's not a challenge to use the same technology even in the UK. So this technology we put into business as usual case, as well as vegetation management, where there's also technology quite advanced, and we decided we would not investigate them further. So the last group is, which would like to investigate further, is detection of unauthorized construction or storage of materials or any other changes around the assets, and land motion and asset motion. They're not as well developed as TRL 5 or 7, as well as they can deliver financial benefits either from saving on the risks or saving on foot patrols to detect any unauthorized construction storage. Next one, please. Okay, so this is unauthorized construction or material storage. You can see we took 2 images at the bottom for one of our substations in Flintshire Bridge, and by using simple algorithm, we can detect where the changes happened between those two images, which is not a rocket science, it's more or less business as usual. The challenge there to identify which of these changes actually caused the risk. If you look in the left top corner, you can see on the left one there is some construction going on, but how is it? And on the top one is just a shade of the building. So how distinguish those different risks and send alarms to our people in operation? Which of these changes made a difference? So in the next phases of the project, we would like to identify, basically develop a risk register and identify how it can be used. And other application and detection of assets or ground motion assessment. So we can use very precise SAR data, which say they can detect difference of several millimeters. So here we would like to understand how it correlates with the real measured data on site, changes to foundation, for example, or land motion that can obviously bring risk to our underground assets like cables or transmission pipelines, gas transmission pipelines. So in the next phase, we would like to test it on the real set of networks, on some of our objects that we know have certain problems, as well as look into those special systems that can better reflect satellite, basically satellite data, and precisely measure changes of the assets. Okay, that's all. I tried to make it short and smooth.
Brilliant, thanks a lot. And just quickly before we wrap up, if the last few presenters want to join, we've got a couple of questions in the chat, so if we can close them off, that'd be really helpful. We've had one for you, John, around Nick's asking about the safety incident triangle and how the ratios between layers compare to other industries such as oil exploration.
Yeah, so as far as I'm aware, the accident triangle is something that's adopted across industry. So it's just something that we've applied to the utility sector.
I had a question as well.
Sure.
As the energy transition starts to ramp up and really accelerate some of the new infrastructure we're deploying, do you anticipate that would drastically change the nature of safety incidents and how we look at them as well?
It's a tough one. Most of the incidents that we saw last year sort of related to safety of the work site itself. So at least 15% of the incidents of the near misses and the unsafe acts last year that SGM recorded at least were related to the barriers not being in the right position. So I'm not sure that it's, I think all the time that there is sort of excavation work going on, particularly in the case with most of the companies that we deal with. I suspect that actually the type of energy that's being used it won't really make a difference if we're dealing with underground assets and excavation. I think that the hazards are mainly from the sort of work environment rather than the materials that they're working with. Does that answer your question?
Yeah, I think it does. That the sort of new technologies we might be using aren't necessarily going to have.
They very well might. I'm not saying they definitely won't. They very well might, but the majority of the incidents, particularly, I mean, we also did a kind of impact versus complexity thing. I didn't show it in this, but really, the risk to the member of the public safety is one of our key concerns, and so working in public, the worksite safety and accessibility is what we're targeting in the alpha.
Alex, for you, there's a few projects in the portfolio which is looking at leak detection in some form and taking various different approaches to it. Have you been able to learn anything from each other, and can you see benefits to looking at how the gas networks are assessing their leaks?
So there is methane detection, natural gas leak detection, which is quite advanced. And we didn't look into that because we consider it as getting to business as usual. What we look into the future, either how we can detect hydrogen leaks, and the sensors that are installed on satellites cannot do that. And what we identified from SF6 leaks, the concentration is too small to detect it. Yeah, probably other projects looking into natural gas leak or methane leak detection, which we did not consider in our project.
Okay, yeah, I got it. We've got a question from Nick on Eye in the Sky and asking if the satellite imagery you're using is no cost. Is it freely accessible?
So there are ESA, the European Space Agency, they have a Sentinel program that they provide free of charge images, although they have very low resolution, and for very precise detection, change detection, they're not used because the pixel is like several meters or I don't know, 10 by 10 meters, that it doesn't make sense. So well, we need to go for commercial service providers that provide images for the cost, because they need to pay off the cost of the satellites.
Got it. A final one for you, John, from Grant. In terms of excavations, is there an element here of subcontracting these types of works and the subcontractors being part of the project too? Is that geared towards you, or is it?
Say that again. So
the question. Here we are.
David, if it's easier, I can ask it.
Please.
Just it strikes me that in perhaps many cases it's not SGN themselves that are carrying out some of these works, the excavation works. There's subcontractors that are doing that. So it made me wonder about whether the subcontractors are sort of reaching into this project or part of the project as well.
Yeah. So field is in use by a number of SGN subcontractors, and definitely, and actually one of the things that we're looking at in the alpha is the kind of it's assumed that when hazards are identified, that the controls that are being put in place to mitigate those hazards, you know, PPE, barriers, protection, all of that kind of stuff, is that they're being put in place to the same efficacy. And actually, at the moment, no one has, you know, real visibility of the efficacy of those controls and it, like how effectively they're being put in place, but also measuring how effectively they help to lower the risk. And so one of the sort of things that we're targeting in the alpha is to provide visibility of that data set for the first time across all field workers, you know, interacting with SGN. So yeah, great question.
Great, thanks. And I think we'll have to wrap it up there because we're running a few minutes over already. One thing that I would want to mention is we do have our final show and tell session this afternoon, which is for the whole systems challenge, covering flexibility and hydrogen deployment and integration. So if you are interested in that, Thomas popped the Eventbrite in the chat. The next step for these projects is the alpha assessments are taking place over the next few weeks, and the selection of the successful projects will then result in kickoff in August of this year, where they then enter their alpha phase, which many of the projects have spoken about this morning. So finally, thank you all to our contributors, for those people asking questions as well, and for your patience and ability to respond, Alex. That was much appreciated. I'm really glad we managed to get through all the presentations.
Thank you all.
Thank you all.
Thank you.
Thanks, everyone. Thanks, Dave.
Thank you.